One of the classic problems where all of this application using the angles measured in radians comes into play, one of the classic problems is the bicycle problem. Now, this is obviously not drawn to scale, but what I have here is a representation of a bicycle. We have the large back wheel, and we have the inner sprocket drive wheel. Now notice these two circles, this is called circle number 1 or wheel number 1, wheel number 2 is the small inside sprocket here. And these are fixed, so these have the same center. So think about whether they have the same arc length or think about whether they have the same angle. Think about that. Radii are all given, and we'll go over that in just a bit. Attached by a chain, so wheel number 2 is attached by a chain over here to, wheel number 3. Wheel number 3 is the front drive sprocket by your feet, and its radii is given. And then that is fixed to a center of the wheel that is determined, the circle is determined by the pedals. So as your feet push the pedals, that causes this outer wheel, there's a imaginary wheel there to rotate, which causes the inner wheel to rotate, which causes chain to feed out, which causes chain to feed in, which causes this wheel to rotate, and which causes the large outside wheel to rotate, and the bicycle runs. Remember that the amount of arc length that this large outside wheel 1 rotates through is the distance traveled. Imagine the wheel is painted, and if the wheel rotates through, let's say, an arc length of 3 inches, 3 inches of pavement will be painted, meaning the bicycle will have traveled 3 inches. And so the arc length, the distance traveled by the bicycle, is arc length S1. Now, all these values are given. I'll go over them real quickly here. Radius 1 is 11. This is obviously not drawn to scale. Radius 1 is 11. Radius 2 is 1.2. These are all in inches, by the way. These are all in inches. Radius 3, the inner wheel is radius 3, is 4.3 inches. And radius 4, the outside wheel determined by the pedals, is 6.2 inches. 6.2, 4.3, 1.2, and 11. I've just picked numbers out of the blue sky. I have no idea. This would probably look like a disastrous bicycle of goofy proportion. Maybe it's a clown bicycle or something. I don't know. But this is my wheel. Let's see. Given the values in the picture, if wheel number 4, so that's the large outside wheel determined by the pedals, if this rotates through 1/2 of a revolution, so if your pedal on your right foot goes from here around to where the left foot was, so 1/2 rotation on the foot pedals, that's wheel number 4. The question is, how far does the bicycle go? How much is fed out from wheel number 1? What is the distance traveled? That's S1. So we're given the angle through which wheel number 4 rotates, and then we're asked to find the distance traveled here. Assume all radii are in inches, it says, and then round your answer to the nearest foot. So be careful when we get our final result here. It's going to be in inches. If you know inches, you divide by 12 to get feet. If I have 24 inches, divide by 12, that's 2 feet. And so remember, our answer is going to be in inches. You're asked to find your answer to the nearest foot. All right, so it's the same structure as before. What are we given? Well, we're given here that the outside wheel 4 rotates through 1/2 of a revolution. We know 1/2 a revolution is pi radians. So we're given the angle of rotation for wheel number 1. So we're given angle of rotation for wheel number 1. We're given, wheel number 4, wheel number 4. We're given the angle of rotation for wheel number 4. And from that, we're asked to find, we find a string of values. The last thing we're interested in finding is S1, the arc length for wheel number 1. Okay, so what can we find if we know theta 4? Well, we can find several things, but notice we have to transfer from wheel 4 to wheel 3 because that gives us the transfer from wheel 3 to wheel 2, and that gives us a transfer from wheel 2 to wheel 1. So that's the flow that we need to handle. From wheel 4, go to wheel 3 and on up the scale. Well, what happens with these two wheels? From wheel 4, wheel 3, they are fixed with the same center. So they have the same angle. The angle of wheel 4 and the angle of wheel 3 are fixed together, are the same. And so if I know angle 4, that's the same as angle for wheel number 3. We could compute S number 4, but that's not needed in the problem anywhere. It turns out that this 6.2 is an unneeded piece of information. That's fine. It's a piece of information that you don't need. There it is. But once we know theta 3, once we know the angle through which wheel 3, this sprocket, rotates, that, because this value, of this circle and this circle are connected with different centers, the arc length here and the arc length here are the same. So we need to find the arc length to transfer. So if we know theta 3, we can use that to compute arc length number 3. We could compute arc length 4, but it's not needed in the problem, so just don't bother with it. A legitimate question is, how do you know which one you need? Well, you need to know which circles transfer to which, and which values are fixed between the two circles. And so in this case, the angles transfer between the circles because the centers are fixed. And so if you know angle 4, which we happen to be given coincidentally in this problem, then all we need from theta 4, we can find angle 3 rather. And if we know the angle for 3, then we can use it to find arc length 3. That's what transfers to circle 2. Arc length, the amount of chain feeding out of the front, is the same as the amount of chain feeding into the back because the chain is fixed. And so that gives us equal to arc length number 2. But if we know arc length number 2, then we can compute the angle through which circle 2 rotates. So we can use that to compute angle number 2. But the circle number 2 and circle number 1, the wheel 2, I'm calling it, wheel 2 and wheel 1, they're fixed with the same center. So the angles translate. So that angle is the same as the angle theta 1. And if we know the angle through which this large outside drive wheel rotates, we can use it to compute the arc length, and that's what we're looking for. So that's going to be our structure. You're going to be glad you have this structure because it's going to be easy to get lost in all this. Just reference this all the time. This is sort of your roadmap, or I guess that's too old school. This is not your roadmap. This is your GPS system here, telling you what to do. All right. So what do we have? We have theta 4. Now we're given half a revolution, but we know that's pi radians. So theta 4 is pi, right? And so that gives us, that's the same thing as theta 3 is pi. So that was a freebie. From that, we can compute S3. So how do we do that? Well, we know S3 is equal to R3 theta 3. And so R3 is known to be pi. R3 is known, where's R3? R3 is known to be 4.3. Theta 3 is pi. And let's go to the machine. All right. I have 4.3 times my exact value. Don't use 3.14. Do not use 3.14. It'll show up in your result. It's not going to be the same thing. Don't use 3.14. Use your value that your scientific calculator has pi. Find it. Go online, do a search. How do you make my calculator find pi? You can find it. Times, in this case, I'm going to do bonk, and there's pi. So I'm going to do 4.3 times pi. 4.3 times pi, try it the third time. I have 13.5088. All right, let's check my results here, 13.5088. Leave that number in the calculator. All right, that's my S3. What's next? That is equal, that's the same thing. You get for free, we get S2. So now we're back here on this smaller sprocket. That's still 13.508 and so on. From that, we can compute theta 2 because we know S2 is equal to R2 theta 2. Plug in the values you know and back solve for the one you want. We need to know theta 2. We know that S3, or S2 rather, S2 is 13.508. All right, and we know the radius. The radius is given to be 1.2. So we want to solve for theta 2, divide both sides by 1.2, write it out. If you don't want credit out of me, if you don't want full credit, then start leaving things out and you won't get full credit. That's great. But if you want full credit out of me, you're going to show me all the details here. And now I'll go to the calculator. I'm going to take the number that I have in the machine already. I'm going to divide it by 1.2. And that's my 11.25 something, 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 something. And I just found theta 2. Where am I? I'm at theta 2. I get for free I get theta 1. And now I'm finally, at long last, out on wheel number 1. I have theta 1. I need to find S1. And so, once again, S1 is equal to R1 theta 1. And S1 is what we need to find. R1 is given. All the radii are given. In this case, it's 11. Theta 1 is the 11.25. And I'm guessing that's going to be a number. I'm going to multiply that by 11 and get about 123-ish or so, 0.83 something something. Okay, so 123.83 something something something. Now remember what units this is. So the guts of the problem is finished. The trigonometry part of the problem is finished. What's left is to satisfy the physics people, because the physics people want your answer to the nearest foot. Everything here so far is in inches. So we have traveled 123.83. This is inches. And the physics people aren't happy with that. Because the boss says we want this to the nearest foot. So if you have 24 inches, divide by 12 is 2 feet. If you have 48 inches, divide by 12, that's 4 feet. So divide by 12 gives you feet. And so we can convert that to S1 is divide by 12, 123, oops, try that again. Let's do that same answer. I'm going to divide by 12. Take that same answer, divide by 12. I get 10.319. This is now feet, and round it to whatever it says. Round it to the nearest foot. So I'm going to round this to the nearest foot. That is 10 feet. So 10.3, that rounds to, we're going to say S1 is equal to 10 feet as our final result. So 1/2 revolution of your feet gives you 10 foot of movement on the bicycle. This explains why, don't make me swear to it, but I believe the only method of transport more efficient than a bicycle in terms of energy input, distance output, is a blue whale, I think. But in any event, our value is 10 feet. Again, you may ask, we use S1, R1, theta 1. We did with the 2, we did with the 3. The question might be, why did we not use S4 equals R4 theta 4? Well, that's because in this particular problem, we weren't given the S for the outside. We just coincidentally happened to be given the angle of revolution for these. If another way to ask the question would be, if this pedal moves 1 foot, or if this pedal moves 12 inches, let's say. Suppose you were given if this pedal moves 12 inches, then the question is, how far does the bike go? So then you would have arc length from which you would compute to angle. The angle would transfer. You would compute arc length. The arc length would transfer. You would compute angle. The angle would transfer, and you can compute arc length. And so it depends upon what you're given and depends upon what you're asked to find as to how many times you go through this computation. That's why this kind of an analysis beforehand helps. Figure out what you're going to do before you get stuck in the middle of the problem trying to do it. And so that's a pretty standard kind of problem, and I think there's a couple examples in the text of working the bicycle problem. And once you've done this through 2 or 3 times, it's the same problem over and over again, and it becomes very familiar and not that much of a challenge for most folks.